Okay, so we're week 3, 213. Jesse and Ryan are in the room, and I was just going to maybe put out a few fires, just to answer some questions from last week's homework, if you got them, and then start looking over some of the material for this week. So a little bit of review from week 2 for a half hour, a little bit of, just look at week 3 together for a half hour, if that sounds good. So you guys want to start with questions, or should I just kind of dig into some...
Let me fire up a little girl here.
I don't think I really have anything.
Let me go over...
I know I probably got one of them wrong last week.
Okay.
I don't remember what
I
it
don't
was.
know how I did. I didn't actually look at them.
All right, and I gotta catch up on grading. It looked like quiz 1 was graded, but I still got to grade like the week 2 homework and the week 2 quiz. And I don't think everyone's done, but we'll get that knocked out by next week.
I didn't think it was overly hard.
Okay. But here, let me go over a couple things. I'm going to do some electromagnetic theory for starters, because I think that was, because we were talking a little bit about how electrons flow, and I was just looking at the discussion board. So let's just look at EM theory. And I'm gonna pop out, and I'm just what I'm hoping to do here is go out to a standard source and just do a little bit of interpretation. So a lot of times you might say, oh, I'm going to go and learn on my own. And then you're like, oh my gosh, what is this person talking to? And so, or about. So I guess I'm hoping that my role in this course can just sort of be the interpreter and putting what is somewhat common knowledge into the context of the course and what we're trying to learn. So let me just go out and look at Maxwell's equations. And we talked about this, I know we talk about this a little bit in 101 when we start talking about electricity. So this guy right here is the picture I want to discuss. You guys seen that before? That like ringing any bells? Like, oh, I don't know what that is.
I've seen it.
Okay, so let's just look at it, because you might look at it and say, okay, I see a bunch of arrows, I see some X's, and I see some dots. But let's dissect that a little bit and figure out what they mean. So I'll do my best to kind of recreate that. So we got these. I don't know why I'm using green today, but I just am. See if this pad will behave for me. Okay, so these circles. Any idea what these circles are? I'm just drawing up. All I'm doing right now is copying that figure.
The poles of a magnet?
In a sense they are, but they're actually just wires in a motor, in a generator, whatever. So it's or a transformer. And you could even look at the cover of your book and say, okay, all they are the cross-sectional areas of the wires. Okay. And I'm putting X's on the bottoms. Any idea why I'm putting X's on these?
I guess you have to have a positive negative.
It's a little bit like that. I'm putting X's on the bottoms, I'm putting dots on the top. And the reason I've got the X's on the bottom and the dots on the top is because if you think about, we were talking about weapons here before, so we might as well stay on that theme for the day. What the heck? Oh my gosh, this is terrible. Anyway, that's an arrow. Thanks for the laughter. Here's the dot, right? The point coming right at you. And then on the back end, you've got your flights, right? So if you look down, down the business end of an arrow, you're going to see a point. If you look at the trailing edge, you're going to see an X. So that's what these X's and O's mean. And that's the direction of the electrical flow. Now, I think we already discussed a little bit in the discussion board the fact that in a cable, so maybe I'll just draw it like this. Here's your cable. Now, if the electrons are actually moving this direction, the current, by convention, is moving in this direction. And I think if you remember back to NRGY 202, we talked about electrons and holes. Well, let's back up even further, because I was trying to go there. Again, what I'd really like to do with this class is somehow not make it seem like, oh, I took this class, and I took this class, and I took, like, I want to make all the classes in the whole curriculum seem appropriate. And this is, 213 and 214 in a lot of ways are supposed to be courses that we send you out saying, yeah, man, I feel good. I know, I remember 102 now, I remember 101, and it's one big, nice body of knowledge. So let's go back to the periodic table. So I'm gonna dig deep, and then I'm gonna come back. So there they are, all 100 and something elements, 92 reoccurring. If we go up here, let's just look. Well, let's look at something really simple for the time being. Here's helium. Actually, I don't want to click on helium. I want to click on the orbitals. Here we go. So we'll start even simpler. There's hydrogen highlighted right up here. And if you look here, you see that you've got a 1s electron. So this is a good way to think about it. The electron itself with hydrogen is pointed up. So the little arrow there, right? If you click on over to helium, there you go, helium. You got one up and one down, and those are just like little magnetic tops spinning around. So the electrons themselves have a magnetic field, and they have a spin. And you can think of them just like little tiny nanoscopic tops. One's pointing up, one's pointing down, and that's just the way the world is. Once you fill up that first 1s shell, you come on up to lithium. The next electron to be added is in the 2s shell. Here's beryllium. The 2s is filled. Here's boron. Now you're in the 2p shell. The 2p shell looks like a dumbbell. See the blue ball and the orange ball? It's a dumbbell. It's shaped exactly like that. The s's are just spheres. So that's where you're going to find that electron in a sphere. Carbon, add another electron in another 2p. Nitrogen gets a seventh electron. Here's oxygen. And you can see those shells filling up. Fluorine, neon. Now you've got 6 electrons in that 2p shell. Sodium hops up to the 3s. And now you get that weird looking dissected ball. But in that ball, you can see that there's the middle orange is the 1s. The next blue is the 2s. And then that outer orange is the 3s. Magnesium. Aluminum. Fun. Here's kind of one of our first conductors. And as we know, a lot of the wiring that we see, even my house has aluminum wiring for gosh sakes. But it's that 3p electron that's the one that's actually carrying the current. It's this kind of free radical way the heck out there in the aluminum with really very little. It's like Pluto. It's like, am I a planet? Am I a meteorite? What the heck am I? And those are the electrons that are actually carrying the current. Okay, so I wanted to show you that. I wanted to show you that you got up electrons and down electrons. That's your quantum theory. keep clicking along. Eventually you get out to copper. Now in copper, your sort of free electron is way out there in that 4s. And again, it's that Pluto-like electron that's carrying the current for you, because it's not really that tightly bound to the nucleus. Okay. So, again, to get back to this guy, the electron itself is flowing that way, and the current flows the other way. And the way to think about current is it's just where did that electron go? Well, it made a hole. Just like cars in traffic, one car moves forward, and now there's a hole for your car to fill it. Pretty simple. I mean, that's all there is to it. That's the electrons and holes. The hole is just where the electron would be if it were actually there. But they move. Now, the other thing to think about is the current itself is traveling just about at the speed of light. You flick the light switch on. So I'm just going to say that the velocity is about c, the speed of light in that direction, and I'm just going to say the electrons are going, I'll just say s for slow. And it's the same way right now, and I was trying to put this in the discussion board. I'm talking and sound is traveling in the room at the speed of sound, but there's no wind at 600 miles per hour. It's just the molecules bouncing off of each other. So you can think of the electrons, they aren't traveling at the speed of light, but the signal through the copper is. All right. So these circles and X's are cross sections of the wire, and the cross sections of the wire are just the same. It's just that copper wire. So if I came in here and sliced these little chunks of copper, I'm going to see circles. Okay, so that's all those are. So the current is flowing on the top. It's flowing out of the page. The arrows are shooting out of the page, and on the bottom, it's going into the page. They're traveling around in these wires, and you kind of think, okay, so this guy comes out and then goes in down here. This guy comes out and goes in down here. Goes out, goes in down here. That's what's going on in your transformers. That's what's going on in your motors. Okay, so I'll get rid of those guys. Now, what the heck is the rest of the stuff? Well, I just showed you that the circles are the electrons flowing in the wire. The arrows have to be something else. What the heck are the arrows?
Flux lines?
They are flux lines of what? So it's either this one, we already covered that, so it's got to be that one. So it's the magnetic field. So the electric field is pouring through the wires. The flux lines, like you said, those are the magnetic flux lines. All right, and I'll do my best to draw them. I'll do my best here to draw them. I'm not going to try to draw all of them, but I'm going to draw this one right here with an arrow. It's an arrow. I'm going to draw another one. Arrow. I'm not going to try to sneak another one in there. I'll just draw a few of them here. I got this one kind of coming off here, coming back here. Arrow. I'll draw another one coming through here. Arrow. Okay, that's probably enough. So, what should I do? Maybe I'll go with the black pen. So these guys right here are E for electric, and these guys are M for magnetic. Now, each one of these circles or arrows coming out of the line is perpendicular to the page, right? And there's, so if this line is, kind of looks like a cheeseburger, doesn't it? So this line perpendicular to page, there's two other lines perpendicular to anything coming out of the page. One is this direction, and the other one's this direction. Because we're in 3 dimensions. We're only looking at a 2-dimensional slice of 3 dimensions. But so in any 3-dimensional space, which is where we live, you can have that direction or that one. Now, it just so happens that most of these lines, like this great big fat one down the middle, is in fact perpendicular to this arrow coming out of the page. Well, look over here. That's actually pointing up, isn't it? So what's happening here is all of these flux lines are actually like somehow simultaneously perpendicular to all of those electric lines. That seems kind of weird, because normally we think of in this room, like, okay, the left wall and the front wall are both perpendicular to the floor, you know, and the ceiling is perpendicular to the back wall and the side wall. And that's all nice and easy. We're all in normal Euclidean space. But here, although those lines are actually perpendicular to the electric field lines. And the reason and what's weird about it at first, but this is the stuff that kind of gets weird and funny, but this is how reality is I'll just try to do a little thing with my hands here. So I've got all the cables are going like this. Any magnetic flux line, like you said, is going to be perpendicular here, but it's also going to be perpendicular here. And so as long as this line, my left-handed finger, is perpendicular to this tube of coils, I'm fine. It could also be perpendicular out here in front. It could also be perpendicular out here in back. So no matter where I am, I'm perpendicular to that cylinder. So the funny thing about the geometry here is that and there's a special name for the shape of those flux lines. Let me show you those. Special name for it. It's a torus. So the magnetic field itself is toroidal. That's another way to say it. Okay. So you got a donut perpendicular to a cylinder. is the way the electromagnetic field works. Okay. So let's. So if we look at this guy, what's even weirder to think about is, let me get back to my. But it's reality. Is this, if we call this line right here, well, let's call this, let's just call that line 1. We'll call this line 2. We'll call this line 3. We'll call this one up here 4. We'll call this one down here 5. And again, this is still 2 over here. This is 1 over here. This is 3 over here. The weird thing about it is at some point way, way, way out in space, line 2 reconnects with itself. Because obviously we're looking at the thing, line 4, you can see the whole thing, but you get far enough out in space and line 2 is actually connected to itself. Line 1, you're like, wait a second, how the heck does that thing connect to itself? Well, nobody really knows, but that's still the way that...
It does.
Maybe it does, at the edge of the universe, wherever the heck that is. Okay, so that's one thing. The other thing I wanted to show you, and then we'll get to some questions here, because I don't want to get too far out of bounds, is whoops, stupid thing always messing me up. Let me get back to Maxwell's equations. Let's look at these. No, let's not look at those. Let's look at these. No, let's not look at those either. I want to show you something that's just kind of that will help you take. I want to help you take that image that we just looked at. I think you guys understand that, right? You understand the electrons are flowing through, and you got a magnetic field. You know exactly what both of those are. But now what I want to do is show, and I think this will help understand some of the equations in the book. Is show that. We'll just look at these guys here for a second. So in this set of equations, and really all I want to do is look at this one. Let's just look at the Maxwell Faraday equation, because it's also called Faraday's law of induction. And really all it means is when you move a magnet, you get an electric field, and when electrons flow, you get a magnetic field. So let's just look at this guy for a second. Del x E equals negative B.
Okay, so the upside down triangle is called?
It's called del.
Del.
D-E-L. Del cross E equals negative, and I'm going to write, I'm going to write D instead of that funny looking D. Actually, now I'll write the funny D, what the heck. Funny D, B, D, T. Okay, so that's Maxwell Faraday. Okay, so let's just dissect this a little bit. We got 1, 2, 3, 4, 5, 6 different symbols going on in here. First of all, what's T? First guess. What's
Time.
Time. Yeah. What's this little del thing? You guys remember, I talked about this a little bit in 102, delta. No problem. That's just change.
So, it's just a triangle?
It's a different, so this one means that we're looking at the change of B, and I'll tell you what B is in a second, it's gonna be pretty obvious as I tell you. We're looking at the change of B with respect to time.
Okay.
Is all. And it's the same thing. So we're going to think about this a little bit like velocity. You know, because in your car, you might have a change in distance with respect to time, and that's how you'd write it. As it turns out, though, B equals the magnetic field. F-I-E-L-D. So, what is the magnetic field? Well, we just drew it. It's all those funny donut lines. Right? And the weird thing is, well, not the weird thing, the convenient thing is, the fact that I used the big B, see how that B is actually a big bolded B? What use the word flux, right?
Yeah,
So-
because
so-
B in the book, well, it looked like the beta in Tesla is known as flux.
So tell me what page you're talking about.
34 or something. Because example for you, compute the flux density in B, but it
Oh,
looks like
good.
beta, not bold.
Yeah,
like
okay.
that.
Right, okay, perfect. So so beta in the book is it's the scalar value. So you can think of the beta in the book as your speed, and you can think about this big B on the screen as your velocity. I think you guys remember the difference between speed and velocity, because if I say, hey, I'm going 55 miles an hour, that's my speed, but you're like, hey, I'm going 55 towards Frenchtown, that's your velocity. Or I'm going 55 towards Helena, now you got, or I'm going 55 straight up or straight down. That's the difference. The big B means the whole field, like what direction is it pointing. The beta just means how strong it is. So that's the difference. They've got the same units, it's like speed and velocity have the same units, but different meanings, because the big B is the whole field, all the flux lines, like we just drew. The little b is just like how big the arrow is, how hard it's pushing. Okay, so all right, so there's your magnetic field, and it's a vector. Now, E is the voltage gradient. Now, what the heck is that? What's it sound like? Tell me what a gradient is, first of all. Just, you probably heard grade or gradient. I mean, tell me what a grade is in road construction.
It's incline.
It's the slope, yeah. So same thing here with voltage. So if I walked around this room with a voltmeter, I'm not gonna have a whole lot of voltage. I start to get it close to the wall over here, it's gonna go up. So E is the change in voltage. It's gonna be high somewhere, it's gonna be low somewhere else. Now, so back in our, oops, back to this guy. Back in our figure, we're going to have very high voltage, where we've got a whole bunch of electrons, and very low voltage everywhere else, right? I mean, that's kind of how all these transformers work. Danger, high voltage, there it is. So the next thing, this X, equals what's known as the cross product and I think I'm going to take a quick Camtasia break. Well, no, I'm going to write the next symbol too, and then I'll take a Camtasia break. And this thing itself is actually the what the heck is it? DEX. It's actually the gradient operator. And here's where it gets a little confusing, but we'll clear it up. Gradient operator. Okay, so I'm going to take a break so this thing doesn't get too long. We're about at 20 minutes, and we'll come back.